In this video, we're just going to quickly get you started with the exercises for the age-structured population lecture. So this is at the end of the age-structured population lecture where it says in-class exercise, age-structured population growth. And there's two different exercises here. One which goes through basic life table calculations in Excel, which should be somewhat familiar to those of you who have already started with Lab 3, so we won't spend too much time on that. And then the second part uses an existing InsightMaker model that you can clone to address some more management implications that result from a age-structured population model. So we'll get to that as well. And let's start with the Excel exercise. So the first thing to do is just to load up this spreadsheet that represents a life table for a hypothetical population. So we're going to save this Excel table somewhere. I'll just put it in my downloads and load it up. So there we go. I will make this a little bigger so you can see it. This life table this life table has, of course, X for age. This is following a cohort through time, so we have 500 to start off in the cohort, 400 left that reached age 1, 200 that reach age 2, so on and so forth. So these are the basic elements of a life table. Of course, we have the fecundity, or the birth rate, and how that changes with age. This is per capita birth rate. And I've already computed survivorship for you, as well as survival rate. All right. And so what you're asked to do is to estimate the generation time, the lifetime reproductive potential, and the approximate intrinsic rate of growth of this population using the information provided here. All right, so you're basically asked to implement this equation for lifetime reproductive potential. So sum up across all ages from birth to the maximum possible age of the survivorship times the birth rate, and then to estimate generation time using this equation here, which we also did in lab, and then to estimate the intrinsic rate of growth, little r, based on this equation, taking the natural log of the lifetime reproductive potential and dividing that by the generation time. So a couple things to note here is that the net reproductive rate, or the lifetime reproductive potential, is it's similar to lambda. So it's like, if this quantity is positive, the population, then every female can reproduce herself within her lifetime, and the population is stable or increasing if this is positive, if lifetime reproductive potential is positive. But it's the difference between the lifetime reproductive potential and lambda is the time frame. Lifetime reproductive potential is essentially on the scale of the generation time. Can a female reproduce herself in a lifetime throughout her entire reproductive years? It's not on the scale of a single time step. Like lambda is usually on the scale of years. So every time you want to update a population from year 1 to year 2, or from year 2 to year 3, you just multiply it by lambda. And so lambda actually has a time frame of a single time step, or a year, whereas R0, or the lifetime reproductive potential, is really on the scale of a lifetime, or a generation. And so that brings up the idea of this generation time and how we can quantify generation time. And it also should make sense why then we take the lifetime reproductive potential and divide it by generation time in order to get or estimate the intrinsic rate of growth, little r, because little r is also on the scale of a year or a time step, not on a generation time. So we have to account for not only the reproductive potential in this population, but we have to take account for the time frame over which that reproduction is expected to occur. Populations with a longer generation time will have generally slower intrinsic rate of growth, all being equal. So that's why we divide by generation time, and that both quantities, R0 and generation time, are necessary in order to compute little r, or the intrinsic rate of growth. So let's do that. Let's refresh our memories about how to implement these equations. The first thing we want to do is to calculate the lifetime reproductive potential. What we have to do is multiply Lx times Bx for every age in our life table. So we have this quantity is equal to Lx times Bx, and we can just copy this down, oops, like that. All right, and that makes it's relatively easy to compute the lifetime reproductive potential now, because we can just take the sum across all ages from birth to the final possible age of this quantity Lx(bx), and that gives us the lifetime reproductive potential of 2.9. So this now represents every female in the population is expected to produce 2.9 offspring within her lifetime. So she's able to replace herself. But she's able to replace herself over what time frame? We do not know that because we have not computed the generation time yet. So in order to compute generation time, we have to make another quantity, Lx(bxx), which is just representing the survivorship for every age class times the birth rate for every age class times x, the actual age. And if we copy that formula down, we can then start computing generation time, which is just this sum of this quantity Lx(bxx) divided by the sum of the quantity Lx(bx). So in Excel, we can do that relatively easily. Generation time is equal to the sum of all these quantities divided by the sum of all these quantities here. And that gives us a generation time of 1.48. So this is saying that the average age of new parents in the cohort is 1.48 years. That's an estimate of the generation time. And with that, we can then compute little r. Oops, that's the wrong. It was autofill. Little r using this equation here. Natural log of the reproductive potential divided by the generation time. And that is a top hat question, so I won't finish that for you, but please answer that and complete the exercise in Top Hat. Next, I would like you to load up an existing age-structured model in InsightMaker so you can clone this model here. So I'm going to open it up in a new tab, Stage Structured Population, and I'm going to clone it. There we go. Okay. So I'm going to clone this model, and the first thing we can know, so this is a basic age-structured model, just like the one we're building in Lab 3. And so you'll see the difference. So let's see, we have births. Only adults in this model can produce offspring. So only the adults are connected to the births flow, and we have a mortality rate associated with juveniles, subadults, and adults. And we can compute the mortality just by taking the total in the stock times the per capita rate. So everything should make some sense here. Make sure that the model makes sense to you before you go on. First step in the exercise is just to start the population off with only juveniles, no subadults, no adults, and see what happens to the population growth over time. So first of all, you see that there's a drop in the population in the first couple of years, and then the population starts increasing, and then it starts this smooth phase, this smooth increase over time. You can see the same thing in every single one of the life stages. Now, when the population starts, you'll see that we initialized all the population as juveniles. So you have everyone in juveniles, there's no subadults, there's no adults. And then you'll see that things change a little bit for the first few years, but again, all life stages reach this smooth growth after a certain number of years, say 6 or 7 years in this case. This is the stable age distribution of the population, right? You have a certain proportion of the population that are juvenile and subadult and adult, and that doesn't change as the population continues to grow exponentially. All these age classes are growing exponentially at the exact same rate, and they maintain this smooth growth over time. So the first question is just, and this is part of Lab 3 as well, is just to try to manipulate the total population size in each of these so that when the population starts off, it's growing automatically right at this like smooth growth. And this is pretty close. What I have here is pretty close. So I want you to just manipulate the different fractions of the population that's in juvenile, subadult, and adult until you get a stable structure, a stable growth. And this is pretty close. And after a little manipulation, I can get something like this, where I have pretty smooth population growth for all three classes, adults, juveniles, and subadults. And of course, that would mean the total population is also growing smoothly at approximately the same rate across time. So that's the stable age distribution. The next part of the exercise asks you to change one of the rates or a few of the rates and see if something changes. So if the stable age distribution changes. So if I change that to 0.3 and I change subadult mortality rate to say 0.2, then I'm no longer at that, like I'm starting off at the same distribution, but it's not the stable age distribution anymore. So you'd have to actually do some more manipulations to figure out what that stable age distribution actually is now. So you can see that now the juvenile and subadult are pretty close together at stable age distribution, and adults much lower. So let's see if we can get something smoother, and that's pretty good. All right, so we now have a new stable age distribution, and we could keep changing that. If we changed our vital rates, every time we change our vital rates, we're going to get a new stable age distribution. All right. In the last part of the exercise, you're asked to change the adult mortality rate to 65%, so a much increased adult mortality rate. Excuse me. And first of all, just see, is this a growing population or is it a declining population? And then imagine we are implementing a population supplementation program where we can release subadults into the wild. How many subadults would we need to be adding to the population each year, or supplementing, in order to maintain a stable or growing population of more than 20 adults? All right. What's the minimum number of subadults that would need to be supplemented in the population in order to maintain 20 adults? So let's see if we can answer that question. Let's go back to our model. I'm going to go to my cloned model here. And so let's make sure we're in the original. We have to go back to our original parameters. This was 0.15, this was 0.5. So let's first move this to 65%. So we're moving the adult mortality rate to 65%. When we simulate, we see the population is indeed declining. All right. When it reaches stable age distribution, it's definitely declining and it's destined for extinction. So the next step is, let's imagine a supplementation program that we have designed a program to captive breed this species and release them at the subadult stage, which means we're going to need to add another flow in this, and this is going to be a flow into the population, and we'll call it supplementation. All right. And this is going to start off at 0, but we might want to add a value slider, and I'll start off with a slider step of 1 and the bounds from 0 to 100. And we can start supplementing this population and see if we can maintain a population of 20 adults or more. All right. And we conveniently have this a plot for adults. If you wanted to make that yourself, you just have to here I can add a new plot, and I'll call it adults 2, and I'll just make sure I'm just going to be visualizing the total number of adults. And that'll be adults over time, because this is a time series plot. So it's going to show adults over time, and so there we go. So I just have to keep on increasing this until I can get my adults to sustainably reach 20 individuals. How many subadults do I need to supplement in this population each year in order to maintain 20 adults? Take some time to work on that and try to figure out what the number is, and when you have agreed on a number with your group, then answer the question in Top Hat. Finally, a discussion point. Is supplementation the best strategy for conserving this population? Just discuss with your group and take a minute to think about how you would go about conserving this population. Is this a sustainable strategy? Is there a better way to go about conserving this population? And with that, I will see you in class this week. Good luck and have fun.